All right, today we're going to pull back the curtain on one of the coolest ideas in tech right now, machine learning. We're going to talk about how we can get a computer to do something amazing, not just follow orders, but to actually learn and see patterns all by itself.
You know, for the longest time, programming was all about giving computers a super specific step-by-step to-do list. But what if there was another way? What if instead of writing out every single rule, we could just show it a bunch of examples and let it figure out the rules on its own? That's the huge idea we're diving into.
And this really is a massive shift in how we solve problems with computers. We're talking about a move away from, manually writing out all the rules to a whole new world, learning straight from the data itself.
Okay, think about something like a spam filter. The old way, you'd have some poor programmer sitting there making this giant list of rules. If the email has this word, it's spam. If it has that word, also spam. But that's super brittle, right? Spammers just get clever and change a word. The new way? Totally different. We just dump thousands of emails into the system, ones we've already marked as spam or not spam, and we just let the machine go to work. It starts to pick up on all these subtle patterns that a human would never, ever spot.
So this whole process of learning from examples that already have the right answers, it has a name. It's called supervised learning. And honestly, the best way to think about it is like you're studying with flashcards. You've got a question on one side, that's our data, and the correct answer on the back, that's our label. We're basically the teacher, giving the computer this stock of flashcards to learn from.
Okay, enough with the theory. To make this really concrete, let's forget about spam for a minute and help out a botanist with a classic problem, trying to identify iris flowers. This is going to be our case study for the whole shebang.
So, picture this. Our botanist is out in the field, and they've got all these iris flowers. They've been super careful, measuring the length and width of the petals and sepals for each one. And here's the goal. It's simple, but it's really powerful. Can we build a little program, a model, that can take those 4 measurements from a new flower and instantly tell us what species it is?
Right, so here's the core of the problem. We're trying to predict a category, the name of the species, from 3 possible options: Setosa, versicolor, or virginica. And the only clues we've got are those 4 numbers from the flower's measurements. That's it. In the world of machine learning, this kind of problem has a specific name. It's a classification task. In this case, a 3-class classification task. Okay, so our botanist has all these notes, but for a computer to make any sense of them, we need to translate them into its language, and that means getting everything organized into a nice, neat structure of clues and answers.
And this brings us to probably the 2 most important words you'll hear in supervised learning: features and labels. The features, those are our clues. In our case, it's the 4 measurements, like sepal length. Think of them as the input. The label is the answer we're trying to get to, the actual species of the flower. That's our output.
And this is what it looks like in practice. See this table? This makes it all real. Each row is just one flower. The first 4 columns, those are the features, the raw numbers. And that last column, species, that's the label, the correct answer that an expert gave us. This table is the exact thing our machine is going to study.
So, we've got our data all set up. But hold on. Before we let our model start learning, we have to deal with a really important question. How do we know if it's actually learning or if it's just, memorizing the answer key?
I mean, think about it, right? If I give you a practice test and then the final exam is the exact same test, getting 100% doesn't mean you've learned anything. It just means you have a good memory. It's the exact same problem for a machine learning model.
And the solution to this is actually pretty clever. We split our data into 2 piles. The first pile, the training data, that's the textbook. The model can study this thing all day long. But the second pile, the test data, we lock that away. That's the final exam, full of questions the model has never seen before. How well it does on that exam is the only thing that really tells us if it's learned anything.
And a pretty standard way to do this is to use about 75% of our data for that textbook, for the training, and then keep the last 25% locked away for the final exam. This way, the model has plenty of stuff to learn from, but we still have a good chunk of new, unseen data to give it a fair grade at the end.
Okay, our data is prepped, our exam is ready. Now for the fun part. Let's pick an algorithm and actually let it loose on the data to find those patterns.
Before we even write a single line of code for the model, just looking at the data can give us this incredible aha moment.
What you're seeing here is called a pair plot. It just shows how the different species look when you compare two features at a time. And look at that. You can see these distinct groups, right? The blue dots, the red dots, the green dots, they're already clumping together. This is a huge clue. It tells us that, yeah, a machine should definitely be able to find the lines between these groups.
So for our actual model, we're going to use something called k-nearest neighbors. And it's a great one to start with because the logic is so simple and intuitive. It basically works on the idea of show me your friends and I'll tell you who you are. To figure out a new mystery flower, the algorithm just looks at the flowers it already knows about in the training data and finds its closest neighbors. For our purposes, we'll keep it super simple and just look at the single closest neighbor. Whatever species that neighbor is, that's the prediction for our new flower. That's it.
Now, for this specific algorithm, the word training is maybe a little misleading. It's not building some complex, artificial brain. Really, all it's doing is memorizing all 112 examples from our training data. It just stores them in a way that makes it really fast to compare a new flower to all the ones it's seen before. The student has studied the textbook, and now it's ready for the exam.
Okay, this is it. The moment of truth. Our model has crammed, it's studied its textbook, now it's time for the final. We're going to give it those 38 flowers from the test set, the data it has never ever seen, and let's see what happens.
And the result? 97%. That's the score it got on its final exam.
So what does that actually mean? It means that for the flowers it had never seen before, our super simple find the closest neighbor model got the species right 97% of the time. That's amazing. It gives us real confidence that this model could actually help our botanists out in the real world.
All right, let's just take a step back and look at the playbook we just ran. First, we started with a clear question. Can we predict the species? Then we gathered our data and organized it into features and labels. Third, and this was crucial, we split it into a training set and a test set. Fourth, we trained a model on the textbook. And finally, we evaluated it on the final exam. This 5-step recipe, this is the backbone for so many machine learning projects out there.
You know, we started this journey with a pretty simple question about flowers, and we ended up with a model that can see the difference between them with nearly perfect accuracy. And this exact same process, learning from labeled examples, is the engine behind so much of the modern world. It's how computers can find your friends' faces in photos, how they can help doctors spot diseases in scans, and even how they can learn to drive cars. So it really makes you wonder, if we taught a computer to see flowers today, what are we going to teach them to see